like I said, we're talking about buckling. So this picture here, hopefully you guys have seen it. Depending on how different columns are supported, that will affect how they buckle. Okay, so that's what this chart is showing. All right, but the one thing that I want you guys to understand is when we have different planes, okay, so when I'm talking about, if you think about your XYZ coordinate graph, okay, you have different planes in that coordinate, right? You have a plane this way, you have a flat plane down here. Okay, so that's what I mean when I say planes, okay? And so when we have any sort of column, okay, so that's where we're talking about buckling. That happens in columns. We were talking about beams before, horizontal beams. Now we're talking about basically vertical beams, which are columns. Okay, when you have some sort of load applied to them, axially, okay, from the top or bottom, that's going to create buckling. All right, so we should have a good idea of what that looks like. But for example, if we have a ruler like this, you guys know if I press on it like at the top, all right, it's going to bend like that. That's buckling. That's all I'm talking about, all right? Does that make sense to everybody? Okay, so with that, okay, buckling can be in different planes, all right? And we want to pick the smallest critical load, okay? So when I say critical load, I'm talking about the load that causes buckling. So, do we want buckling in our beams? If we design something, do we want a beam to buckle? No, right? So we're obviously trying to avoid that. So that's why I say the smallest, we're going to pick the smallest critical load, just like when we did in chapter 1.
This is where I connect current concepts to previous concepts and introduce any equations that the students will need.
Okay, so if there aren't any questions, we're going to start with the first problem. So, like I said, we have two pieces right here. Okay, so the first thing that we want to do, they're saying we have two rigid bars, AC and BC, and they're connected at the pin at C. We talked about this, okay? So knowing that the torsional spring at B. Okay, so what is a torsional spring? Have you guys seen a torsional spring before this class? No, okay, so if we think about a regular spring, okay, it has a spring constant, right? And then when we're trying to figure out the force created by a spring, so F spring, it's K times what? X, the distance that is compressed or stretched, right? So the same concept is going to apply for a torsional spring. It's still going to have a spring constant, okay? But instead of preventing axial movement like a regular spring does, a torsional spring prevents rotational movement. So if I'm trying to rotate my whatever this way, the torsional spring right here is going to prevent, it's going to resist that movement just like an axial spring would. Does that make sense? So the distance instead of X would be what? Theta, right? Because that's the distance that the spring is moving through. Okay, so that's the only thing that changes. All right, so we have that there. And then they say determine the critical load for the system. All right, so we basically want to figure out what this P is that causes the system to start to bend, to start to buckle. Okay? That's what we're looking for. All right, so the first thing we want to do is just set up a free body diagram of the whole system. Okay, so free body diagram of the whole system. So, and we want to draw it in the buckled position, not in the position that it's at right now. All right? So we have down here, we have our torsional spring, okay? And instead of an axial force that our linear spring causes, what kind of force are we going to have for our torsional spring? A moment, right? Okay, because a linear spring creates an axial linear force. Torsional spring is going to create a moment, right? It's going to be resisting rotation. Rotation is a moment, so to resist that moment, we need another moment, okay? So we're just going to call this M spring that's down here at B, okay? What else is happening at B, forces-wise? BX and BY, right? So we're going to do that as well. BX, BY. Okay, and like I said, we're going to draw it in the buckled position, so we're going to draw it bent like so. Okay? Is this an exaggerated position, do you guys think, or no? Yes. Yeah, it's exaggerated, right? Because pre-critical happens right when it starts to bend immediately, yes?
How do you know the direction of the moment?
So I'm just making an assumption, right? Just like we've always done in statics and back in the beginning of the class, you make an assumption, you solve through math, and if it ends up being wrong, it'll just have a negative sign in there. All right? Does everybody hear that question? So if, how do I know which way the moment for the spring is going? We just make an assumption just like always before. All right? Okay. So this is obviously exaggerated. This is not how much that it's going to buckle. We're looking right when it starts to buckle, but we're going to draw it exaggerated so we can analyze it. All right, so this angle right here, we're going to call theta, okay? And then what's happening up here at A? P, so I have P that we're trying to solve for, okay? What else? Yeah, so I have a reaction force from A, all right, not Y because it's supported on the sides, all right? Any questions about that? Okay, so from here, we're just going to do our sum of forces. So sum of forces in the x direction equals 0. This is my positive direction. So what do we have, guys? Just ax plus bx equals 0. All right, that's what we got there. We got sum of forces in the y. That's going to be our positive direction. So we have by equals p. All right, and then lastly, we want to do our moment. Where do I want to take my moment about? What do you think would be a good spot? B, anything else? C, okay, anybody else? A, all right, okay, so.
Questions?
Yes?
What do we do with the spring on top?
This is not a spring, it's just a roller.
Oh.
Yeah, but we only have our springs down here, so the springs are usually going to be shown in red. All right, so that's our torsional spring down here. That's just a roller. All right, okay, so some people said B, and then some people said C, and then some people said A. All right, we're gonna do B, right? Why? Yeah, it's got a bunch of stuff that I can get rid of. What, right? So what can I get rid of there? Bx and By. Okay, so do my sum of moments around point B. So we have our spring, that's going to be in the positive direction, so the moment from our spring. And what else is creating a moment? AX, okay. So positive or negative? Negative. Okay, times what distance? L. Why would I not figure out what that dotted line distance is? Because it's not really L, right? It's bent, it's a little shorter. Right, because we're still saying that this was really, really, really small, right? A really small angle deflection. So when that angle is really, really small, that length is pretty much approximately L. So we can make that assumption in these problems, okay? You don't have to start doing trig. All right, has everybody got that? So we can just do times L, all right? So AX times L equals 0. Okay, so we get M of the spring equals AX times L. Can we simplify this a little bit more? What do you guys think I can do with that M spring? What did we talk about? Yeah, okay, so we know for a linear spring we can change F spring to K times X. Okay, we can do the same thing that we talked about before with our torsional spring. We said that it was K times theta. Okay, so we have K times theta over L is equal to AX. Okay? Does that make sense to everybody, what we've done so far? Any questions? All right, so can I solve for P? What do you guys think? Can I solve for P? At this point. Do I have stuff to solve for P? No, right? Okay, because I have AX, so I can solve for BX, right? But I can't solve for BY, so I can't solve for P. So I'm not there yet, okay? So the next step is we want to break apart our column and do a free body diagram of a smaller piece, okay? So should I break it up and do BC? Or should I do AC? Why do you guys think I should do AC?
Because you know AX.
Because that's where P is, right? That's what we're trying to solve for. So we're going to use that one, all right? So we're going to do free body diagram of our AC portion. All right, so still same thing. We're going to draw it deformed. Okay, we have our P right here. this distance is, or this angle is still theta, okay? And then we still have our AX right here, okay? What else? Do I have everything? What do you guys think? Yeah, right? What do I have at C? Y'all said it earlier. We have a pin. Anytime we have any sort of pin, we have reaction forces there as well if we remove that pin and see what's going on there. So we're going to have reaction forces at C. What are they going to be? CX and CY. Awesome. CY, CX. Okay? What is this distance right here? L over 2. All right. Okay, so we're going to do the same thing. We're going to do our sum of forces for our x equals 0. All right, so we got there CY equals P. Okay, do a sum of forces. That's not x's. Why don't you guys say anything when I do stuff wrong? You just going to let me do it? All right, so that's going to be AX equals CX. All right, sum of forces in the y, that's where we get our CY equals P. Okay, so those are pretty straightforward, but it doesn't help us, right? So last thing we can do is our moment. So where should I do my moment? C, right? Same concept as before, okay? We want to get rid of CX and CY. We don't know what those are. We don't really need them. They're not helpful to us right now, so we're trying to figure out P. All of those reasons go into why we're going to take our moment around C, okay? Everybody get that? All right. We're trying to find P. Always just keep that in mind. So sum of moments around C equals 0. All right. So tell me, guys, CX and CY go away. So if you want to start with AX, for example, what's the moment created by AX? So yeah, it's going to be negative, and then it's going to be AX times what? Times L over 2. Okay, what about P? What's the moment arm? It's this, right? So we're going to call this X. All right? We don't know what that distance is, right? It's probably some small distance, but we don't know what it is. Okay? How can I solve for this X value? Trig, right? All right, well, I know you're like, well, I thought you said that I didn't have to do trig, right? Well, hold on. Okay, so tan theta, we know is equal to what in this triangle? X over L over 2, right? Okay, well, what have we always done in this class when we have tan of theta? It's just theta, right? Because we said it's really, really small. If you do tangent of theta of a really small theta in your calculator, you will get a really small number. It's still approximately the same thing, so we can say this is approximately theta. All right, so what we're just saying is X is equal to theta times L over 2. Okay? And if you guys remember, this is very similar to what we did with our triangle in the last session. Yes?
Didn't you just do L over 2 sine theta, and since it's a small angle, sine theta equals theta?
Sine theta equals theta?
Yeah, with very small angles. Like cosine theta with small angles equals 1. Sine theta with small angles.
Yeah, I mean, you can do it whichever one. I mean, I like to do it with tangent because it's straightforward because we can see the triangle and go through, but you can do it with anyone. Okay, all right. All right, so now we know what X is. It's just theta times L over 2. So now let's figure out our moment for P. Positive or negative? Positive. Okay. What did we say the moment arm was? X. So it's going to be times theta times L over 2. All right? So we get... Okay, when we simplify that out, all right, so our L over 2's can cancel, right? So we're left with P times theta equals our AX. Can I solve for my P critical now? Yeah, right, so I had AX in terms of K theta and L, and I know now that this is equal to K theta over L. My thetas cancel, so we get P critical is equal to K over L. Okay, does that make sense to everybody? It's going to be the same solution process for all of these types of problems. You're just going to do free body diagrams till you get the P critical that you're looking for. All right? Questions? Okay.
For sessions with over 100 students, there are a few key methods you saw me use to communicate certain key points to the students. Those consisted of asking questions or posing the incorrect answer and then asking the students to explain why it's incorrect. I also gave the students time to think and respond when I asked a question, as well as I repeated the questions that students asked me. Along with a clear speaking voice, one of the key things you will see me do is writing down important things I have just said. This is one of the most effective ways to get students to retain information you may have just said to them. As I work the next problem, you will see me use these communication tactics again.
All right, so for this problem, still buckling, okay, but it's a little different. This is rigid body, all right? We don't have any pins or anything like that where in the middle where it can bend, where it can move, okay? This is just a rigid column, all right? For these, you need to make sure you read the problem statement because they might give you some really important information. Okay, so they tell us column ABC, that's this one, has a uniform rectangular cross-section with these dimensions. The column is braced in the XZ plane at its midpoint C. Do we think that that's important? Yeah, okay, it is super important. So we're going to underline it. Okay, so the column is braced in the XZ plane at its midpoint C. So here we're talking about planes. Okay, this is why I brought up planes at the beginning. All right, so that's going to be super important to see where these planes are and where the buckling is happening in these planes. All right, and they say it carries a centric load P of 3.8 kilonewtons. Knowing that the factor of safety is 3.2, determine the largest allowable length. Okay, so as you guys can see right here, they're talking about L. All right, so that's not the overall length of the whole column. That's where they have labeled L. Does everybody see that? Okay, so when they say L here and L here, it's talking about from here to this midpoint. All right, that's important too. That's kind of what trips people up on this problem. All right, and then they tell us use E equals 200 gigapascals. All right, so they told us that we have something braced in a certain plane. All right, and one of the things I told you guys at the very beginning was we can have buckling in different planes. Okay, and the reason that we might need to look at that is if things are braced differently when you look in different planes, or if we have different moment of inertia, because remember I is in our equation, our P critical equation. If we have different moment of inertias, that will change our buckling as well. Okay, do you guys remember from chapter 4 when we looked at moment of inertias about different axes at the very end? Yeah? Okay, we're doing that again. All right? Okay, so the first thing that we want to do, okay, is we want to look at the different planes that we have that are parallel with our column. Okay, so in the vertical direction is what I mean when I say that. And analyze, see what the buckling is in each plane. Okay, so we have two different planes here that we can look at. We have our X, so if you guys see that's labeled here, we have our X, Y, Z axis. Okay, so we have our X, Z plane, right? And this is why I brought colored pencils. So our X, Z plane is going to be this one, all right? This is our X, Z plane, okay? So in this direction, 3D, okay, along that plane, that's our XZ plane, okay, XZ plane. All right, and I know that because this is my x-axis, this is my z-axis. So this plane is in my xz coordinate area, okay? Does that make sense to everybody? All right, so the other plane that we have is our YZ plane, okay? So our Y is going this way, Z is still vertical. So this is the other plane that we need to look at. Can everyone visualize these planes? Do you guys understand and see what I'm talking about? Because it's really important to see these planes. That's the only way you're going to be able to understand the buckling that's happening in each one. Say yeah, no, okay, all right. All right, so we're going to look at each plane, all right? So we're going to start with our XZ plane. All right, so that was our red one that we did first. All right, so if you guys look at the picture, I'm going to look directly at my XZ plane, okay? So I want to be looking at it just straight on. Okay, so when I'm looking at it straight on, the face that I'm going to see of my column is this one, this smaller one. Okay, does everybody see that? That's the one, this is the face that's parallel with that plane. Does that make sense to everybody? Yes? Okay, so that's what I'm going to be drawing, as if I'm looking at it head on like that. All right, so that's what I'm looking at. This is my B distance right here. Okay, so questions so far? All right, so what did my problem statement say about this plane? It's braced at the midpoint C. Okay, so that's this thing right here that's going through right there. So at our midpoint C, it's coming out of the sides of our rectangle, right? So what that means is at this center point, it's braced. So can it buckle at that point? No, it's braced. So we're keeping it from buckling, bending outwards, all right? So it's braced here. All right, now I want you guys to go back to your original front page, okay, that has this picture on it, all right? So we always want to figure out what type of end connections our column has. So what do you guys think this might be? The first one, second one, third one, or fourth one? Okay, first one, that's our fixed end and free end. What else? Anybody think that it is D? Okay, what about B? Raise your hand if you think it's B. Okay, raise your hand if you think it's A, because I didn't ask that one. What about C? And y'all don't know. What we have going on here, all right, free means, looking at this one first, free means that there's nothing there holding it down, okay? If we look back at our column, is there something here? Is there something here? Yeah, there's something there kind of restraining it a little bit, so it's not free, okay? So it's definitely not this one, all right? So the other thing about this one that you guys want to notice is fixed. Oh yeah, sorry. What fixed looks like. We know what fixed looks like. It's directly attached to a wall of some sort or ground or whatever, right? Is this directly attached to the wall or ground, or is there something right there? There's something right there which kind of looks like that, right? A pin, okay? Just because it doesn't have a little hole and a little gray circle doesn't mean that it's not a pin, all right? Because we either have free, fixed, or pin. Those are the only three options that we can have. Okay, and we know what free and fixed looks like, right? Yeah, we just talked about it. Okay, so what is this one? B, okay, because it's pinned at the bottom and pinned at the top. Okay, so that's this one. So we know that L effective for this is going to just be L, okay? It's just going to be the length of our beam, and we can see how it bends. Okay, it just starts bending at the pin and bends all the way down to the next pin, okay? All right, so that's how this one's going to be.
So even though you can't bend around that like reinforced bar, it's still...
We're getting there, we're getting there, all right? So, pin, if that bar wasn't there, it would look just like this, right? Right? Okay, so, but the bar is there. So do we think the bar is a fixed support or a pin support? Fixed. Okay, so fixed means that it restrains movement in any direction, right? Can I move in the other direction? Did the problem say anything about the other direction? No, right? Which means that I can move in the other direction. We're going to get to that in a second. Okay, but since it told me that it was only braced in the XZ plane, that means that it's not braced in the other plane, which means that it doesn't restrict movement in all directions. Okay, does that make sense? So is it fixed? No, what is it? Pin. Okay? So that means that we have a pin here, pin here, pin here. Okay, so basically all it's going to look like, if this is the center line of the beam and I'm drawing how the center line of the beam changes, it's just going to curve kind of like an S, kind of like we had two, if we just had two pins put right on top of each other, okay? Just like that. All right, so it's just like we have two pin beams right on top of each other. Does that make sense to everybody? Yes? Okay, so that's what it looks like. All right, now I'm just going to draw the rest of the stuff that we know. We know this is L from here to here. We know this is L from here to here. All right, so this axis this way is which one? What is it? X, right? Because that's, I'm looking at this face right here. This is the one that's parallel with that coming out of it. Okay, and then we have our Z coming out of the top. All right, so what axis is coming out of the page that we don't see? Y. All right, so that's super important. We'll get to that in a second. Okay, yeah, that's all we want to talk about for that one right now. All right, so now we're going to look at the other plane as well. Okay, so now we're going to look at our YZ plane. So that's our blue one. All right, so I'm going to erase kind of what I did earlier. All right, so back to our original picture. Okay, the blue plane is our YZ plane. So we just said that our B side of our rectangle is what's parallel to the plane that we just talked about. So which side is now parallel to our blue plane? Which side? The D side, right? This side, this bigger side right here, is the one that's parallel with this plane. Okay, so that's what we're going to be looking at straight on. Do I draw my brace in the middle? It's not restricting any movement, right? Another way that you can look at it is if you look at this side, it's just coming out of the side like that. Okay? So we can still move left to right. This thing right here coming out of the page is not restricting any of that movement, and the way to confirm that is because the problem didn't say that it was. Okay? Does that make sense to everybody? All right. So we're going to go through the same process. Okay? So what did we say these ends were? Pin, pin, right? So this one's going to behave the same way, except we don't have this brace in the middle, so it's fully free to move right there. Okay, so it's going to come out just like that, just like we talked about our pin, pin looking, just like that. Okay? Does everybody see that? Okay. So what axis is this coming out of the out of the side? Y, right? And this one's our Z. So which one is coming out of the page on this picture? X. Okay. We want to label the rest of our lengths. This one's L. This one's L. Okay. So now that we know what buckling looks like in both planes, okay, we can see that it's different. Okay. We can now see that since it's different, we're going to have to calculate P critical for both scenarios. Okay. All right. So that's what we're going to do. So remember our equation for P critical was pi squared EI over L effective squared. All right. For P critical, do I plug in 3.8 kilonewtons?
No.
No, what do I plug in? 3.8. Okay. Why do you guys know? What factor do I have to use? Factor of safety, right? Because they told us the load is P 3.8 kilonewtons. Okay, but we need to take into account our factor of safety to figure out what our P critical is, okay? Because P design, so that's what they gave us, okay, is equal to factor of safety times P critical, or P critical over factor of safety, okay? So P design times factor of safety is equal to our P critical, okay? So that's what we would plug in right there. Does that make sense to everybody? Okay, and you know to do that because they gave you a factor of safety. All right, so P critical is equal to 3.8 kilonewtons times 3.2. So it is equal to 12.16 kilonewtons. All right, so now we know what our P critical is. Okay, reminder, what are we solving for again? L, right? Okay, so we have our P critical. We need to find L, which is in this L effective, right? Okay, so the other things that we need is our E. They told us that. So the last thing that we need to find is our I. Okay, so I, we remember our moment of inertia. Where do we find that from? We can find it from appendix. What type of geometry do I need to look at to find my, my moment of inertia? The cross-sectional area, right? A rectangle, right? We look at the cross-sectional area, so that's exactly what we're going to do here. We're going to look at our cross-sectional areas of our beam. So basically we're going to cut them open and look down just like we've always done. Okay, so if I'm cutting this beam and looking down, this is my B length right here. So that means that this is my D from here to here. Okay, what axis did we say was coming this way? Now think about it. Which axis is that way? X, right? Okay, and that makes sense because this one is parallel with this short side right here. That's what we talked about up there. It matches, it follows what we said, so we're good to go. Which axis is coming this way? Why, right? Because I talked to you guys before. We were looking at it this way. And so the axis that we said coming out of the page from right here was Y. So that's what we have to draw coming out of our B side is Y. Okay? All right, so this is our Y. Okay, so this is our axes. This is what we're labeling our sides. We remember I talked about chapter 4, you can have different moment of inertia depending on which axis we're rotating about, right? So we have to pick which axis we're rotating about, either X or Y. Okay? So I want you guys to remember we said that Y is coming out of the page right here. Okay? So which way, I'm trying to figure out how you guys can see it. So it's coming out of the page. Which axis is my beam rotating about? If you put your hand on your picture and follow the curve, where's your hand curving about? Y, right? If I follow this curve of my beam, it's curving this way, right? That's what we drew. Everybody can see that? Okay, so it's curving this way. Y is coming out of the page. My hand is curling around my Y axis. Does everybody see that? Okay, so if you're a visual person, that's how you can figure that out. If you're not a visual person, it's always going to be rotating about the axis coming out of the page, coming out of your picture. Okay, so it's rotating about axis coming out of the plane of buckling. So if we're buckling in the XZ plane, we're rotating about which axis? The Y, the one that's not in the one out of those three that's not in what I just said, right? So YZ plane, which axis are we rotating about? X, okay? And same thing if you want to visualize that. Again, your hand's curving this way. This is how the beam is curving. And we said that X was coming out of the page. It's curving around our X axis. Always it's going to be like that, okay? We have the plane that the buckling is happening in, and then the axis that the buckling is rotating about is the other one coming out of that plane. Okay? So here we're rotating about your Y axis, and here we're rotating about your X axis. Okay? All of these things are super important to getting to the right point. All right, so are there any questions? Yes?
In the first picture, you have them going both directions. One goes, the buckling went left and one, yes.
This one?
Yes. Does it really matter which one goes?
No, you're saying if I wanted to draw it this way?
Yeah.
No, right? All we need to understand is that that buckling point in the middle is fixed. So we don't have buckling right there. That's all you need to understand. That it curves and stops in the middle and then curves again. It can go either way. We don't actually know, right? I just made an assumption. Okay? All right. So we know which axis it's rotating about. So now we can figure out what our I is. Okay, so I'm going to draw my cross section for this one as well. Same way we did before. Okay, this is my B dimension. D going this way. All right, so which axis is this? Y, right? So which one is this? So Z was going vertical, right? So now we're looking down. So which axis is this? X, right? Okay, can everyone see this? Yeah? Yes? No?
Yes.
All right. Are there any questions? Okay, so now we can find our moment of inertia. So this one's going to be IY. All right, so for a rectangle, we know it's 1/12 BH cubed. So B being the base. All right, so don't get confused by this, the fact that they called B one of the sides B. It may not be our base, okay? What's the thought process? How do I know which side to put in as my base? The one that's parallel to the axis I'm rotating about, right? So in this one, I'm rotating about my Y axis, right? Okay, that's this one. So which dimension is parallel? D, right? This is going to be my base dimension. Okay, it's going to be the one that's parallel to the axis I'm rotating about, okay? Let me check and make sure. Right, okay, so if you forget that, I'm not going to write it down. We have it written down right here. All right, B, the base okay, is a dimension that's parallel to the axis we're rotating about. Okay? So that's why it's important to know which axis we're rotating about. Okay? All right. So that's our base. So that means that our height is going to actually be this B right here. They gave us these in the problem, 12 and 22. Okay, so IY here is going to be equal to 3.168 times 10 to the negative 9 meters to the fourth. Okay, we do the same thing here. This one, since we're rotating about our x-axis, is going to be IX. Same equation, 112 BH cubed. All right, so what's my base dimension in this problem? B, right? Because that's the one that's parallel to the axis I'm rotating about. I'm rotating about my x-axis, so I'm going to pick my B dimension. Okay, and that makes my height D cubed 1.0648 times 10 to the negative 8 meters to the fourth. Okay? All right, so we said we're trying to find L. We go back to our equation. We know what E, we know what I is, okay? But we need to look at L effective, because L effective isn't necessarily the same thing as L, right? We talked about that at the beginning. It comes from this chart, okay? L effective is equal to different things in different scenarios, right? Okay, so we said we're looking at B, we're looking at pin. So here this says L effective equals the length, okay? And I want you guys to notice, they say L effective equals L, okay? When they say L here, they mean the distance from one pin to the next. Does that make sense to everybody? Okay, so they're talking about the distance from where we start buckling to where we come back to our neutral position. All right, so if we go to this one right here, if we go right here, L effective for this one, all right, what is the distance between where we start buckling and we come back to our neutral position? L, right? Because we can start here. Okay, we have buckling, and oh, look, we're back at our neutral position. So it's L. Does that make sense to everybody? All right, everyone understand why it's not 2L? Okay, all right, so it's L because we start here to pin, we have buckling, we're back at our neutral position. That distance was L. Okay, so our L effective for this one is just going to be L. Okay? All right, for what about this plane? What's our L effective for this one? 2L, right? Because we went from where our pin started, okay, and then when we come back to our neutral point, our other pin, and in this scenario, because they called L half of the beam, well, then we have to call it 2L, okay? So don't get confused by that, all right? Because I know this problem is on Chegg, and people are like, why is it 2L? Does that mean that it's fixed free? No, okay? This is why it's 2L, all right? I'm just saying this because I'm pretty sure at least one of you in here has looked at this and seen that, at least, okay? All right, so our L effective for this, but you guys knew it, which is awesome, is going to be 2L. All right, and that is, again, because we're starting at our pin, going back to our pin, neutral position. That length from here to here is 2L. All right? Okay, so we have everything that we need to know to find our L, this L right here, this L right here. Okay, so we're going to plug into our equation. We know that P critical is equal to 12.16, all right, kilonewtons, so equal to pi squared. E is 200 gigapascals. Okay, and I want to point out to you guys, you need to change these units, right? What do I need to change this to? Okay, it needs to change to newtons. What about this one? It needs to go to pascals, okay? I don't do all of that in here just because I just want you guys to understand the process, but please don't think that you don't have to change them, all right? All right, so we know what our I is. So that's 3.168 times 10 to the negative 9 meters to the fourth over our L effective squared. For this one, we know that L effective is equal to L, so it's just L squared. Okay? So for this one, when you simplify it down, and make sure I'm doing the right one, okay, you get L is equal to 0.717 meters. Okay? All right, so we're going to do the same thing for this one. I kind of ran out of space, you guys. All right, so sorry about that. All right, so we're going to have the same thing. Okay, we're going to have P critical, which is 12.16 kilonewtons, equals pi squared, 200 gigapascals. Okay, we're going to use the I that we found for this one, 1.06, 10 to the negative 8 meters to the fourth. All right, so I'm just pulling that from there. Sorry, it's really small. Okay, over our L effective, which is 2L. So what is that going to be? 4L squared, okay? So then we solve for L again, and you should get 0.657 meters. Okay, so I got two L's. Which one should I use? The smaller one, right? Because what this thing is telling me, okay, is in my, we're going to pick the smaller one. This thing is telling me that in this plane, all right, at the load that they gave me, anything bigger than 0.657, I'm going to have buckling. Okay? So I might not have buckling in this other plane over here, but it doesn't matter. It's still attached to each other. It's all one column. All right? So when we apply that load, we're going to have buckling at any length larger than this. So we got to pick the smallest one, just like we've done before. Okay? Questions? Yes?
Why we use the case B
Yeah.
from here? On the very first one in the XC plane. Why didn't we use case C? Because you said it goes from a pin to a fixed point, because we said that the bar going through it is fixed.
Okay.
Why wasn't the pin fixed?
So I may have confused you guys by saying fixed just by meaning at that point it's not moving, all right? But we talked about, remember, they just said that it's braced in the XC plane, right? So my YZ plane, the other one, right? This one right here, okay, the beam is free to move at this point. Okay, so when we have something at a certain point, it can move in one direction, but maybe not the other. That's a pin. Fixed, like a fixed, like this one or this one, restricts motion all in all directions. Right? Okay, so that's why it's not fixed. Okay? So how are we feeling so far about buckling? Great. I'm glad y'all are feeling great. All right. So, those are the only two problem-solving processes that we've got for this chapter. The first one that we did, where we do our free body diagrams, okay? And we solve for P critical, for non-rigid, okay? You can have a few different problems. You guys can look in your textbook. You can do them. You can have springs in different places. The lengths can be a little different, but that's all that can really change, okay? And then we can have things like this. All they can do is change up the different ways things are braced, all right? So that's all that's happening here. This problem we're going to approach it the same exact way. It just looks a little different because it's braced a little different, all right? Okay.